All right. 45 minutes is really a short time for a talk, so let's get going so we don't get too late. I'm Björn Fahller. I'm here to talk to you about higher order functions for ordinary C++ developers. This is not a super advanced talk, but could be interesting. I think C++ developers usually don't use higher order functions very much. There are good historic reasons for this because it's been a pain. A bit of background, I guess I'm becoming one of the old graybeards in this business. Writing software has been my profession since '94. Wrote my first C++ program, I think, in '93. I'm not entirely certain of that. Most of my career has been in embedded systems, although since a few weeks back, I've started a new career. I'm working for a star counter in Stockholm with in-memory databases. This talk is not about databases. So, higher order functions. So, what I'm going to do now is I'm going to give you a very brief intro to higher order functions. And then I'm getting into an example. This example will be from the embedded world, because I kind of guess that is where most of you feel at home. And also because especially developers don't like, historically, these kind of constructions for fear of bloat. And then we're going to look at C++ 17 optional and a really cool extension to it that may or may not become standard. I don't know. We'll see. So, definition, higher order function. A higher order function is a function that takes other functions as arguments or returns a function as a result. Within the scope of this talk, whenever I say function, I mean anything that is callable. It can be a lambda, it can be a function pointer, whatever, something that is callable. Who here has used higher order functions as per this definition? Who's never used them, ever? A few hands, okay, you're in for a treat. Who's written any? Who's never written a higher order function? A few hands, good. You'll go away from here much wiser in 40 minutes, cool. So, here we have an example of a higher order function from the standard library, stood none of. So, we're saying that if none of the elements in the vector match this predicate, this lambda, then we do something. And none of is a higher order function because it accepts a function, in this case a lambda, as one of its parameters. So since a few of you had not seen these before or even less written them, let's have a look at how to implement none of. It's not very difficult. A typical higher order function is a template. So in this case, none of takes an iterator pair and a predicate, something that is callable. And we iterate over the elements, and if the predicate matches one of the elements, we say return false because the function is none of. None should match. And if we get through the entire loop without the predicate ever triggering, we say true. Okay? Nothing fancy. You can be super fancy and do SVNA stuff to ensure that predicate is actually callable with the value type of iterator, etc. But standard library doesn't. So why overdo it? It doesn't really make sense to write none of because you have it in the standard library, but just to show how you can do this. And then we continue with our program. We write some more stuff. We have another algorithm from the standard libraries that any of. Also take something callable, in this case, a lambda. Everything clear so far, nothing very surprising. Would you be surprised if I say that I really find this code annoying, super annoying? Can you guess what it is I don't like about it? It is highlighted in boldface. Hint. We have, for all practical purposes, the same lambda repeated twice. Sure, one of them has the hard-coded constant 0, the other compares with the variable num, which is captured, but it's essentially the same lambda. And this annoys me. I don't like that. I don't like repetition. So can we do anything to get rid of this repetition? One thing we can do, hold on tight now, we write a function. C++14 gave us the auto-return type to functions, which makes it possible to return lambdas. And if there's only one thing you will remember from this entire talk, make it this. Make it remember to use the auto-return type to return lambdas, because that enables so many cool things. So now I have my function equals, it returns a lambda, so I can get rid of some of the repetition. At this point, there is someone who asks, what about std function instead of auto-return? And these are not really the same. To begin with, std function does, one of the things that it does is type erasure. So you don't have to worry about what anything is, but the type erasure is not for free. So calling something via std function is a lot of overhead. Sometimes that's perfectly okay, sometimes it's not at all acceptable. But let's generalize. Why only limit ourselves to an int? We can call it with anything. And you may notice now also that the lambda uses it's a generic lambda that uses auto for its parameters. So it can be called with anything. It doesn't have to be the same type as the key is, as long as they are equality compatible. With std function, that is not the case at all, because I cannot say that I want a std function that returns a boolean is callable with anything that satisfies some criteria that is not known outside. So, for example, if I call this function equals with a const char star, a string literal, you will not be able to call the returned lambda with, or the returned std function, if that is what you use, with a std string, because a std string is not a const char star and it's not implicitly convertible. So these are not really the same, even if you don't care about the overhead. So use the auto-return type to return lambdas. So now I can write code like this. If none of the values in v equals 0, and then later on, while any of the values in v equals num. That is much easier to read code, I think. And an advantage of this is that you can now have an argument with your colleagues about what it should be called. Should it be called equals? I usually get some nervous giggles when I say that, because, well, naming, bike shedding. But actually, when you're arguing about what to name something, you're trying to build a mental model of what does this thing actually do, and how do I best explain that to someone else? I do that by choosing a descriptive name. You're familiar with Matt Godable's Compiler Explorer, I presume. Let's have a look. The horrendous overhead of this construction. I wrote any of here instead of none of, but you recognize it. And I have the equals higher order function here that captures, it's templated, captures a number, and I'm just returning whether any of the values in this vector. So we can look at the result. We get begin and end, compare if they are equal. If they are equal, we're done, return 0. If they're not equal, compare what the iterator points to with what we got as a parameter. If they're equal, go to 5, return 1. Otherwise, add 4 because that's of an integer. See if we're at the end. If not, one more revolution. There's no overhead in it. You cannot write this more efficient. So that is good. But let's see what happens if we try std function instead. Whoa. V table. Wow, it's so much. Exceptions. Std function is not for free. If you need the functionality that it offers, by all means, don't be afraid to use it, but it's not cheap. So prefer, if you can, just use the auto return type to return a lambda. All clear? Right. Let's get going. That was a very, very brief intro. I hope you got the gist of it. So let's get an example. I used to work for NetInsight in Stockholm. NetInsight makes networking equipment. An obvious thing to have in networking equipment is to deal with IP addresses. So let's have a type for dealing with that. I prefer to have one that I can construct from 4 bytes because it makes test code much easier to read, and of course a constructor from a full value. If you think I'm weird for writing my own type for an IP address instead of just a 32-bit integer, come to my type session tomorrow. Then we need a net mask, which is sort of an IP address, and I want to be able to do bit masking with an IP address and a net mask. Nothing strange. So now I can write a function, a higher order function, IP matches, that takes the address I'm searching for and a mask that defaults to compare the entire address. So I capture the address I'm searching for with a mask, and it's callable with some other address, and we check if the masked address is equal to what we were searching for. And here's a good time to look at this cheat sheet that Twitter account WalletFox posted. Be very careful when you write higher order functions where the higher order function takes some parameter by value. If your lambda then captures this by reference and you return the lambda, you have a really good foot gun here, because the reference will refer to the parameter that has long gone out of scope. You don't want that. So if you capture parameters, if your higher order function accepts parameters by value, make sure you capture by value. This is important. Right, so with this, we can now use it as, in this case, I'm just removing all addresses in the 192.168 subnetwork. This is, I think, reasonably readable. But then, of course, in networking equipment, we have IP interfaces. So we have, this is obviously super simplified, but just to illustrate, we have some state. We can have an interface turned off or on. I can call setState. This must be an outline function because it will communicate with the IP stack, depending on, it might actually even talk to hardware. But I want to be able to query the state, and this is inline because I cache the current value. And of course, I have functions for getting its address, its netmask, its gateway, and some other things. And now we have a situation here. I showed you just a couple of slides back this higher order function for matching IP addresses. And here we have an IP interface. It has an address on its own, and we also have the gateway that is an address. And maybe I want to be able to match addresses, search for IP interface with a certain gateway or whatever. So how can I make this work without writing specific code? I should be able to reuse my function for matching IP addresses. So this is a generic thing. If I have a function f1 that takes a y and returns a z, and I have another function f2 that takes an x and returns a y, I want to be able to compose these to get one function that calls f1 with the result of calling f2 with x. For example, if f1 now is IP matches and f2 is some select address function that, given an IP interface, returns its IP address. How can I do that? This is not difficult. Again, it's a function template. It takes two function times f1 and f2. We use the auto return type from C++14 to return a lambda that captures these functions. And when called with anything, we return the result of calling f1 with f2 of x. Generalizing this to any number of functions is more difficult, but in this case, this is trivial. So I can now use this as such. So I want to find something, find an IP interface that is the composition of IP matches and select address. IP matches you saw earlier. Select address is a function that, when called with an IP interface, it calls the .address member function and returns it. So this will, in effect, for every interface, it will call select address to get an address, get that address into match IP, and we're done. And of course, why not take this composition and make it usable in other places? So lift it out, write a function address matches that takes an IP address and a net mask and returns this composition using, again, the auto return type to do this. And then I can just use this new address matches function in my find if. I think this is neat, don't you? And then let's go on. We can write, of course, select gateway and select state and select mask and what have you. These are simple things. So maybe I want to compare more than one criteria. I want to find an IP address, an IP interface which has an address in the 192.168 subnetwork that is off. So how do I write a when all to compare all these higher order functions, their results? How can I write this? In 17, this is really easy, C++17, and we're on C++18 now, so of course you're all using C++17, right? So I'm using a variadic template where the predicates can be any number, and I'm using the fold expression. Are you familiar with fold expressions? Or who's not familiar? Okay, I will not make this a lecture on how fold expressions work, but I can through this particular example. The return here in the when all function, when it's parenthesized like this, this will expand to PS of x is call of the first predicate and logic and ... and ... are all the other predicates. So if we had 3 predicates, it would be the first predicate of x and the second predicate of x and the third predicate of x, and we get the normal logic short-circuiting. In this case, we have only 2, so PS of x and ... is address matches, logic and state is. Cool. And address matches you saw before, state is of course composition. Obviously, it's you've seen the equals on the very first few slides, and select state is obvious, and we compose these. So we can check if the value returned from calling the state on an IP interface is equal to the value we're searching for. Nothing strange there. And we can go a bit further. Now I'm actually going a little bit too far. I'm a bit insane here, but generally don't be insane. But there is a purpose here. Don't worry. So I want to say that for all elements, all IP interfaces in this vector V, when both the address matches 192.168 subnetwork and the state is off, then I want to turn it on. Sorry. So I can write an if-then. You should see, you recognize the pattern. It's the same as always. It's a function template that takes a predicate and an action. We use the auto-return type to return a lambda that captures the predicate and an action. And if the predicate is true, then we call the action. In this case, maybe I overdid it, but why not let the action be allowed to consume value by perfect forwarding if it wants to? Yeah. So you see what's happening here. The predicate will be this composition of when all, and action will be set state. And set state is, of course, also a higher order function that uses the auto-return type to return a lambda that captures the state we want to set. And when the lambda is called with an interface, we call the set state member on it to set the value that we want it to have. So, you're with me? Or is everything completely weird? Let's have a look. Is this expensive? Who wants to venture a guess? Huge overhead. Lambdas, higher order functions, templates. Okay. We have the equals, you saw that before. We have an IP address, net mask, masking operator. We have the IP matches, higher order function. The IP interface, class, select address, compose, select state, set state, the address matches composition, state is composition, when all. A little bit difficult to see over here, but yeah, looks the same. If then, the same. So then I have a function here. Actually, I shouldn't do this. I should do like this to make it the same as the example. So we loop over all elements. If address matches state is off, then we call set state on. Okay, this function is a bit big, so we need to save register values on the stack. We get our begin and end. If they are equal, we're done. So that's boring. Otherwise, we get the address, compare with a mask if it matches, if it is what we're searching for. If it isn't, we add 16, that's the size of the struct. Check if we're at the end. If not, we take another revolution. If, on the other hand, the address did match, we compare offset 14, that is where the state variable is, 14, 12. Offset 12 to get the state variable. If it is 0, we jump to 3. What happens at 3? Yeah, we set a 1 to ESI, and we call set state. That is cool. Then we add 16 again and go another revolution. There is no code bloat. You cannot write it much more efficient than this. That is cool. So, yeah, and at the end, of course, we need to restore the registers from the stack. I think this is neat. We get an enormous expressive power by using functions and composing functions, and it doesn't cost us anything. So don't be afraid to use higher order functions. Right. Now we're going to sort of a different stage of this presentation. You're familiar with optional T in C++ 17? Oh, not many hands. All right. Yeah, I'll explain it. Don't worry. Stud optional T is a class template that manages a value that may or may not be there. So this is, like I mentioned, it came in C++ 17. There's nothing C++ 17-ish about it at all. You can easily write it in C++ 11 if you want to. And there are various open source libraries out there that implement this. This is super useful in lookup functions. Say, give me the route for this address. I say, no, sorry, don't know, don't have it. Or actually do have it. A minor inconvenience is that as stud optional is defined in C++ 17, T must not be a reference. You can get away with it, just work around it by saying that you use reference wrapper to T, and then you're good. So I'll show you how to use this. I have a lookup function here that takes an IP interface under predicate, and it returns an optional reference wrapper, so that if nothing is found, we return an optional that doesn't hold anything. But if it is found, it returns an optional that refers to the IP interface that we found, so that I can call member functions on it. So its use is typically something like this. I get my variable found from the lookup, and I say, if it is found, do stuff with .value of it. And this is quite useful. The cost of this is that the stud optional contains a Boolean variable, a member variable. So you get that extremely small overhead. Enter this young man, Simon Brand, Tartan Llama on various social media. He has his own optional on his GitHub account. It builds with C++ 11. And it actually supports references out of the box. By the way, the reason that the standard optional does not hold references or does not allow reference types, as far as I know, is that it can be a bit confusing what it means to assign to it. Do we mean that we assign a value to the variable that is referred to, or do we mean that we rebind the reference to refer to something else? Simon's version, when you do use it with a reference, is rebinds it on assignment, so that it refers to something else. But his optional also has some functional style extensions, and that is the reason I want to talk about them, because those are neat. And he actually wrote a proposal for standardization for this. And I understand that he is currently writing on, I don't know if he's getting an R1 or if it's a completely different proposal. Do you know, Tony? No. Yeah. Anyway, he's working on a revised edition on his proposal for a functional extensions to optional. We'll see where that lands. Personally, I hope for this because it's neat, but you never know. At least I don't. The way you use it is this. You include TL/optional, TL for Tartan Llama. And here I can use it with a reference type, int reference in this case. So when I default construct it, it does not hold any value, it doesn't refer to anything. But when I assign it with an int variable, it will rebind to refer to I, now it has a value. And if I say the dot value that is a reference to I, then we assign to I. If I assign it with another int variable, it rebinds the reference to refer to the new variable. That is not too exciting. What is exciting is this. These functional continuations. So you can say v dot and then and something that is callable. This something that is callable will be called with a value held by the optional if it holds a value. Otherwise, it does absolutely nothing at all. Likewise, you can say dot or else, which will be called if it doesn't hold anything. In the first case here, this is a void function, so v stays undefined, uninitialized, doesn't hold a value. But it's also possible, like in the last line, to return another value, another optional that will replace what was in there, which is super useful because now you can use this in a lookup function. Say, look up this dot or else. That is neat. Also, it is a little bit neater than this. Did you notice the difference between these two slides? So here we have 3 separate statements, but by changing it to use the dot continuations, I say v and then dot or else. So you can change these. And the cool thing with that is that if you have a bunch of and thens, for example, if one in the middle fails, then the ones that follow will not do anything. And you will know at the end that, no, the operation failed. Didn't get what we wanted.
Start with and then call it, right?
No, you don't. Okay, the question was, I have to start with a dot and then. No, I don't have to. You can start with dot or else. I'm not sure it's a very brilliant idea, but you can. So let's use this, see what happens. So change my lookup function very, very slightly so that it returns a Tartan-Lama optional of an IP interface reference. And we have some func that does something if our lookup succeeded. But since we have these continuations, we can do this much cooler. Look up this interface that matches 192.168.1.1, and then do stuff. This is neat. And like I mentioned, we can also return something that itself is optional to be able to fail an operation. So I can say that set state, and then I've changed set state so that it returns an optional, so that that is its way of signaling that, sorry, I could not set the state for whatever reason. So then I can say, or else, write an error message, or well, whatever, something. And this is neat, I think. It's a very powerful way of composing functionality in a somewhat different direction from what I first talked about. So let's again have a look at the overhead. There is actually an overhead in this one, but that I think is a missed optimization bug in Clang. I'll see if you agree with me. So here I'm including Tartan-Lama optional. We have the lookup function. I changed it to use std puts instead of cr because it makes much easier code to read in Compiler Explorer. Push state, get begin and end, see if we're already done. This is cool. It already got what this address was. If we're equal, go to 4. If not, add 16, another revolution. Then we check if we are at the end. If we're at the end, we leave. Then for some reason, I cannot really fathom. I'm not very good at x86 64 assembly, to be honest, but as far as I understand, this is a null pointer check, which doesn't make any sense whatsoever, because it won't be. I'm guessing the reason is that an optional that is an optional to a reference is actually has a partial specialization that is implemented in terms of a pointer. So it knows if it holds a value if the pointer is not null. I think that's where this, as far as I can see, completely redundant null pointer check is done. But if it passes this, then we call set state. And go to 7 where we pop the stack. And in the other cases, if we either fail to look up or if well, my set state was trivial, so it always succeeds, so it doesn't have any check on this one. If it fails, we call puts with this failed string. Neat, eh? And with this, I'm pretty much done. We talked through my extremely long, winded agenda here. We saw in the beginning some higher order functions. Some are completely generic, like e equals and compose and then. That actually didn't strike me when I first started writing this presentation that they were. It was something I noticed while writing the presentation that, hey, these are completely generic library functions. And then we have our domain-specific functions. IP matches, select address, set state, what have you, and our domain-specific compositions like address matches and state is, and so on. When I realized that the ones on the left are completely generic library functions, I started scouting the internet for cool libraries for higher order functions in C++, and to my surprise, I did not find a single one. I presume my Google foo was failing. But that was actually the case. I did not find any. So I wrote one. Feel free to use it if you want to. Be aware, though, that I may have gone a bit crazy on that one. It's fully const expr and fully variadic. You can, and the functions can take any number of arguments. And it's a compiler bug magnet. I filed four compiler bugs on the compose function alone, and that's because the only reason it's only 4 is because I haven't bothered with Visual Studio. But by all means, if you want to toy with it, do so. But that was true then. After, in April, Boost 1.67 was released, and it has a library Boost Hoff higher order functions, which I haven't really worked with, so I cannot say that much about how good it is. What I can say is that the overlap between Boost Hoff and my Lift library is almost nothing. Actually, it's only Compose that is the overlap. Boost Hoff has a number of other really cool stuff for currying functions and rearranging the parameter order and whatever in functions. Also, Boost 1.68 was released just a couple of weeks ago, so it might be a good idea to look that one up. But as far as I could see, Boost Hoff hasn't had any change in its functionality. Maybe there are bug fixes. So to summarize, key takeaway messages. Use the auto-return type. I lost count of how many times I said that. I presume you will remember it. Write functions that use the auto-return type to create lambdas and return them. Be careful with the capture, right? Capture, if your higher order function takes parameters by value, capture by value. This is important. Write functions that access or modify your state. Like the select state and set state member functions that or higher order functions that I showed. And compose functions. And give these compositions names. And yes, bike shed the names with your colleagues, because that is good for those who will read the code further down the line. And the functional extension to optional, I really hope we get that in the standard, but if not, we can use Simon Brand's implementation. And I should mention expected. Optional is you get a T or you don't. Expected is you get a T or an excuse, E for excuse. Say why you didn't get a T. So it's sort of like a stud variant, but it has an opinion of what you should have, what you should not have. Expected, it's always 2 types only. And that's it. There you have again the link to my library should you want to, and you have information about how to spam me if that is your thing. Thank you for your attention. Three minutes for questions.
When you write a higher order function, there's a question on how you should pass the predicate, for example, into the function by value or by forwarding reference.
Yep.
So STL chooses by value, but
yep.
that was made before.
Yep.
Do you miss optimization opportunities if you don't forward these arguments perfectly forwarded into the lambda?
Okay. For the higher order functions that accepts functions as parameters, the standard library takes them as by value. And the question is, do we miss optimization opportunities because of this instead of accepting by reference, I presume? Maybe, not that I've seen, but maybe. But there is another thing, and that is if your higher order function actually holds a state and it is not copyable. Say you have a higher order function that holds a unique pointer. Then it's not copyable. Then you have to move it. Okay, you can move it, sure. What I did in my lift library is that all of these are using perfect forwarding. So if you pass them by value, you get a copy. If you do a move, you get them moved. To the specific question of missed opportunities for optimization, I have not seen it, but that is not a guarantee that it won't happen. Other questions? All right, thank you again.